For such a short problem written in the textbook, this one's pretty deceptively difficult. The reason it's deceptively difficult is because when you react formic acid, this is formic acid, plus sodium hydroxide, um, both of them go away. You don't have either thing anymore. Um, this is a weak acid and this is a strong base. And you get water and you get sodium formate, which is Na. I always write this formula wrong. HCOONA. All right. By the way, if you're wondering why I put the Na at the end, it's because that's actually the acidic proton. The hydrogen attached to the carbon, there's not a very large electronegativity difference between this, so this is covalent. On the other hand, what happens here is that the oxygens, the two oxygens, are so electronegative that they draw the electrons away from hydrogen and makes it much easier for the hydrogen to break off as H+. In other words, the oxygens suck the electrons away, the hydrogen doesn't have any electrons, it becomes protonated, it falls off, it's an acid now. So that's why I put the Na at the end. That's the hydrogen that falls off. The other hydrogen doesn't. In any event, let's getting back to the original point. If you're at the equivalence point, it means the acid's equal to the base. There is no acid, there is no base, there's just this thing, and water. And if you remember anything about this rule of thumb, I keep saying you gotta remember, weak acids make basic conjugates. That's a base. All right, the reason that's a base is because it can go and react with water, COONA, I forgot the H in the front, plus water. And what can happen is it's a basic acid, so it's a basic salt, so it can actually pull the hydrogen away from water. And when it does that, you form HCOOH plus NaOH. By the way, we can rewrite this equation without the NAs because on both sides the NAs are positive and they're free floating in the water, so the net ionic equation actually just gets rid of the NAs and just writes the fact that that's negative and positive, negative. So the on both sides the Na is exists there as an ion and it's dissolved, it's aqueous, so we can get rid of it. Everything else stays. This is that plus water makes, I should really have an equilibrium arrow going on here, formic acid plus OH. Right. So just to recap, this is a basic salt up here. The sodium formate is a basic salt because it can dissociate in water and make OH, hydroxide. In other words, it's a base. It makes OH in water. Even Arrhenius would call that a base. If it makes OH in water, it's a base. So, lots of complicated things going on then. In other words, this problem doesn't really have anything to do with this or this. It has to do with the fact that this salt can undergo hydrolysis. It can react with water. All right. You might recognize that when you got this kind of situation here, actually an ice table is what you're going to want to use, because this is an equilibrium and we're really going to want to set up an ice table. So I'm going to set up an ice table underneath this equation. So here's where I messed up originally. When I originally did this problem, I said, oh, it's stoichiometry. It's 0.10 molar of the sodium formate, because obviously one of those and one of those makes one of those. And I was absolutely right if we were dealing with moles. But if you're dealing with molarity, which obviously has to be in the equilibrium expression, it's actually not 0.10 molarity. Really what it is that you have, let me get an eraser here if I can. I'll just use white pen to pen it out. Anyway, what you really have here is that when you added the acid and the base together, you doubled the size of the solution. Here's why that's a problem. It means we would be completely right to say 1 mole of this and 1 mole of this, will come together and make 1 mole of salt, but this would be 1 mole per liter. Let's pretend it's 1 liter, and this is 1 liter. In other words, the volume actually doubles. When you add a liter and a liter together, you're going to get 2 liters. And if you get 2 liters, well, that's 1 mole per 2 liters. In other words, that thing has half the concentration that you would expect. It has a concentration of 0.050 molarity. Whoa, yeah, that's the thing that messed me up. All right, we don't care about water. We care about that and that. They're both 0 at the beginning of the equilibrium. You're going to subtract an x, you're going to add an x, and you're going to add an x. And so this is going to be 0.050 minus x. This is going to be x, and this is going to be x. All right, now we need a Ka. I'm going to go to a new sheet just so that I can do this. All right, actually, I misspoke. You can't use Ka. Why? I don't see any H plus in this equation. Do you? I don't see it. I don't see H plus. I don't see hydronium. I see OH. Actually, in this one, OH. And if we have OH, that means really we're not supposed to use Ka. We're supposed to use Kb. All right, here's why we're supposed to use Kb. Because Kb is equal to OH times the conjugate acid, whatever that is, over the base. So the base and its conjugate acid, which is Hb. All right. Well, in this case, the base is really the HCOO thing, and this is the formic acid. And so OH is there. All right, so let me plug in the symbols from the ICE table. It's X and X for those two things at the top, which you know is going to be X squared. And at the bottom, we have 0.050 minus X. All right, that's going to be all equal to Kb. Well, you can go look up Kb. I looked up Kb. It's in the same table on page 680 as I got the last thing from, 680. And if you look up Kb for formic acid, it's 5.9 times 10 to the negative 11. All right, so let's plug it all in. So 5.9 times 10 to the negative 11, x squared over 0.050 minus x, and let's rearrange it to get it in the nice algebraic form that's going to make this easy to solve for. Times 10 to the negative 11x minus 2.95 times 10 to the negative 12. You do have that nice quadratic formula program on your calculator, right? Because it makes it really easy to solve for x. It's 1.72 times 10 to the negative 6. And let's remind ourselves that OH is x. So that's actually equal to the concentration of OH. Well, we don't care about OH, we care about H. But luckily, for pH, we can get to pH 2 different ways. One way we can get to it is that we can find OH from the fact that H plus and OH is going to be the same thing as Kw, which is 1 times 10 to the negative 14. All right, so you can solve for it that way. You can plug in that number and solve in that equation. That way you can get H, and then you can solve for pH. All right, that's not the way I'm going to choose to do it. I actually just want to find POH, because I know that an even easier equation is that pH plus POH is equal to 14. So if I just take the negative log of this number, I'm going to get the POH. So negative log of that is equal to POH, and so therefore the POH is, I got 5.77, and so therefore subtract it from 14, you get the pH, and so the pH is 8.23, and that's the pH. If you weren't able to do this problem, you really should do another one. Do number 35, but don't do all of them because it's long and difficult. Just do D. D is a pretty similar problem to this, and I'll give you a hint the pH at the end of the whole thing should get you 8.79. All right, so that's pretty similar to this problem. Just do it.